What if a massive solar storm hit the Earth? Imagine a typical day on planet Earth. Skies calm and blue, people moving about their routines, untroubled by the cosmic forces at play just beyond our delicate atmosphere. Satellites orbit serenely, relaying signals that keep the heartbeat of our digital world in steady rhythm. Communications, navigation, weather forecasting, global finance, all quietly dependent upon a network of technologies whose lifeblood is the uninterrupted harmony between the sun and our planet. However, hidden behind the warm light and familiar patterns, our star sometimes stirs with a violence so profound that it reaches across millions of miles. And then, from this vast nuclear furnace, something extraordinary occurs. A massive solar storm is unleashed and hurled directly toward Earth. Long before the blast reaches us, the first murmur of danger is detected by solar observatories, both in space and on the ground. Scientists note a sudden, intense flare on the sun's surface. A cascade of X-rays and ultraviolet radiation erupts from a complex tangle of magnetic fields. Solar flares, immensely powerful bursts of energy, are a warning shot, but it is the coronal mass ejection that follows, a colossal belch of charged particles and plasma that poses the greatest threat. This immense bubble of electrified gas, potentially containing billions of tons of matter, travels through the vacuum of space at millions of kilometers per hour, swelling and racing along lines of invisible magnetic force. As the sun's energetic eruption unfolds, scientists spring into action, alerting institutions and agencies around the globe. Space weather forecasters analyze the data, calculate velocities, and estimate impact windows. Headlines begin to circulate. A major solar storm is on its way, one that could rival or even exceed the infamous Carrington event, the powerful geomagnetic storm of 1859 that lit up night skies with auroras and disrupted telegraph systems. But the world in 1859 was one of horse-drawn carriages and paper records. Today, the electronic nervous system of civilization is everywhere. Much of humanity remains blissfully unaware as the solar storm travels the last few hours or minutes across 93 million miles. But emergency meetings are called, routine satellite maneuvers are canceled. Astronauts aboard the International Space Station are directed toward shielded compartments. Power grid operators review contingency plans. Airline routes are rerouted to avoid polar overflights. And then the wave arrives. The first to hit is a barrage of solar radiation, energy that bathes the Earth's upper atmosphere, inflating the thermosphere with heat and causing it to swell like a balloon. Radio communications in the high-frequency band, HF, flicker and falter, especially near the poles, where energetic particles shower down along magnetic field lines. Long-distance airline flights over Arctic regions lose radio contact and are forced to divert. GPS signals, so carefully calibrated to fractions of a second and centimeter, become erratic, undermining navigation for everything from transoceanic ships to precision agriculture tractors. Moments later, the true force of the event arrives in the form of the coronal mass ejection, the invisible shield of Earth's magnetosphere, our planet's defense against the charged onslaught. Buckles under the impact. Enormous electric currents are induced in the swirling geomagnetic storms, spiraling along the field lines and into the ionosphere. Around the world, the visible night sky is transformed. Auroras erupt at latitudes far lower than usual. Brilliant rivers of red, green, and purple dance across skies in latitudes as far south as the Mediterranean, the southern United States, northern India, and Australia. Onlookers marvel at the beauty, perhaps unaware that these lights portend an invisible unease. As the storm collides with infrastructure built for another era, one of relative solar calm, consequences begin to unfold. The most immediate, and potentially severe, is the enormous current induced in electrical power grids. In the 21st century, vast networks of metal wires and transformers crisscross continents, linking power plants, substations, and homes. Under normal circumstances, subtle interactions with Earth's magnetic field are little more than a curiosity. But a geomagnetic storm of this magnitude can drive currents that far exceed design tolerances. In control centers from Quebec to Scandinavia, from London to Tokyo, alarms begin to blare. Transformers, some weighing hundreds of tons, overheat and fail catastrophically. Power stations trip offline to prevent overload. Cascades of shutdowns ripple across interconnected grids. In just minutes or hours, cities plunge into darkness. Traffic signals wink out, subways grind to a halt mid-tunnel. The hum of industry and commerce dissipates. The enormity of such an outage is difficult to comprehend. In our modern world, electricity is the keystone. Water pumps, sewage treatment, food refrigeration, hospital life support, electronic banking, and communications all depend upon it. Emergency backup generators fire up, but diesel supplies are finite. Fuel transport and distribution infrastructure can themselves be paralyzed without power. Cell towers and internet routers equipped with battery backups keep the world connected, but only for a time. Meanwhile, the effects high above the Earth are just as profound. In orbit, satellites are bombarded by high-energy protons, risking hardware malfunctions and loss of control. Some satellites are forced into safe mode, their sensitive instruments powered down in self-preservation. Others, unable to react quickly enough, succumb to failure. Instruments fried, solar panels degraded, orbits perturbed by the swollen, more resistant upper atmosphere. Global positioning systems suffer outages and errors. Earth-observing and communication satellites blink offline. Back on the ground, air traffic control scrambles as planes lose navigation signals, and radar is intermittently disrupted by ionospheric interference. Aircraft flying on polar routes are most at risk, exposed to higher doses of cosmic radiation. Emergencies are declared, flights are rerouted, passengers and crew subjected to procedures hastily crafted for a scenario deemed unlikely. Banking and finance, built on the backbone of secure, timed communication protocols and digital transactions, shudders as the global digital behemoth grinds down. Automated teller machines and credit card processing terminals flicker into darkness. Trading floors are paralyzed. The international flow of money, debt, and assets slows to a crawl. In a frighteningly short span, the economic heartbeats become irregular. Water and sanitation quickly become critical. Water treatment plants rely on grid electricity to purify and distribute water. Without sustained power, reservoirs and elevated tanks empty, and the taps grow silent. In cities, waste treatment falters. Raw sewage becomes a problem, not just an inconvenience. Hospitals, heroic in their response, rely on backup systems, but must triage patients and resources. Ventilators, dialysis machines, refrigerated medications, all must compete for dwindling generator time. The most vulnerable, newborns, the elderly, those on life support, are at greatest risk. Over days and weeks, the full scope of the solar catastrophe spirals outwards. Utilities assess the damage to electrical transformers. Some, by design, are robust enough to survive. Others are catastrophically damaged and must be replaced by components that are rare, massive, and require months or years to manufacture. Without long-distance power transmission, even those regions spared total darkness must ration electricity. The ripple effect grows. Food supply chains, reliant on cold storage and just-in-time delivery, slow to a trickle. Supermarket shelves empty. Rural communities fare better, relying on wells, local farms, and stored resources. Cities, vast engines of consumption, struggle to sustain themselves. Law enforcement and emergency response are strained to their limits. The sudden leap into a world without power, light, and communication triggers widespread anxiety and, in some places, panic. Curfews may be enacted. Volunteers and professionals alike mobilize to deliver aid, maintain order, and reassure the public. Community centers are repurposed as emergency shelters and food distribution points. Amid all this, some industries surprise with resilience. Amateur radio operators, hobbyists who communicate using equipment independent of the internet and cell networks, spring into action, relaying critical messages for emergency services and communities alike. Local networks of goodwill coalesce as neighbors band together, sharing food, water, and warmth. With time, engineers and planners work to restore order. Grid operators reroute power, bringing undamaged sections online first. Portable generators and temporary transformers are airlifted in from less affected countries. Privately owned home solar systems, if equipped with the right technology, provide islands of power. A reminder of the value of localized, distributed energy in an uncertain world. But for some, the journey back to normality is measured in weeks, months, perhaps even years. Replacing a high-voltage transformer is not the work of days. These are immense bespoke devices, built to order and requiring specialized labor and materials. Economies take years to recover to pre-storm performance. Some companies, especially those whose core business relied on continuous data flow, are unable to weather the interruption and disappear. Amid the hardship, there are lessons. Governments convene inquiries. Scientists testify about the need for increased investment in space weather forecasting, in grid resilience, in the hardening of satellites, and critical infrastructure. International coalitions form to prioritize the rapid manufacture and delivery of replacement components. Society adapts in both subtle and profound ways. The experience of sudden technological vulnerability leaves a mark. Like the memory of a great earthquake or flood, it becomes an enduring part of cultural consciousness. Families invest in emergency supplies. Cities revisit their disaster preparedness plans. Remote villages, once seen as backward, are lauded for their native resilience, knowledge that becomes newly precious. In the longer term, technological innovation surges, as it often does in the wake of disaster. Next-generation transformers are designed to withstand swings in geomagnetically induced currents. Satellite electronics are more robust. Orbits and control protocols are adapted to allow rapid safe-mode responses. Power grids are subdivided into smaller, more resilient microgrids, capable of isolating faults and preventing continent-wide blackouts. Critical services, water, food storage, healthcare, are equipped with more reliable and renewable backup options, from solar to wind to fuel cells. Governments collaborate on international response protocols, recognizing that space weather knows no borders. Yet not all consequences are technological or economic. A great solar storm, like any global crisis, changes how people see themselves, both as individuals and as part of a broader planetary community. The luminous auroras, glimpsed over streets and farmland far from the poles, serve as a reminder of the cosmic stage upon which humanity exists, a planet, tiny and fragile, shielded by invisible forces and dependent on the goodwill of its star. Communities discover both their vulnerabilities and their strengths. In the early days, as the world waits for news and reflects by candlelight, some rediscover joys and practices long put aside. Storytelling, communal meals, the calm of a night sky unspoiled by artificial lights. Children gaze upwards, inspired in awe and curiosity by the celestial spectacle. Scientists and educators take the opportunity to teach a new generation about the sun, earth, and the intricate dance of magnetic fields and cosmic energy. Historians note, too, that the Great Solar Storm became a pivotal event. It marks a before and after, a point at which high-technology civilization realized the need to look skyward, not just in wonder, but in vigilance. Space weather forecasting, once a specialty, becomes a routine part of news. Alerts about solar activity are as familiar as weather reports about hurricanes or blizzards. Investments in solar storm simulation and preparedness become just another facet of responsible governance. Economists study the aftermath for years to come, quantifying losses, tracing disruption through global supply chains, ensuring against future risks. The insurance industry finds new markets in solar storm protection policies for infrastructure and businesses. Research universities launch programs in solar physics, magnetospheric science, and disaster-ready engineering. The psychological scars fade with time, but for a generation, the memories linger. Memories not only of struggle, but of extraordinary beauty in the glowing sky, of neighbors helping neighbors, of a planet-wide event that for a brief moment erased borders and united all beneath the unchanging sun. But why are such events so rare, and what exactly makes a massive solar storm different from the more routine, smaller ones that the Earth endures each year? The sun is a seething ball of plasma, undergoing cycles of activity every 11 years or so. At its peak, solar maximum, sunspots multiply, and with them, eruptions become frequent. X-ray flares and coronal mass ejections range from modest to magnificent. Most of the time, Earth dodges direct hits. The geometry of the ejection, the timing, the shape of our magnetic field, all combine to limit direct impact. But a truly massive event, like that of 1859, or others recorded in ice cores and tree rings, occurs only once every century or two. These are solar storms with enough energy and the precise directionality to truly challenge Earth's defenses. Scientists have studied the risks of Carrington-level or greater storms for decades, and the consensus is sobering. Such an event, if it occurred today, would cost trillions of dollars in damages, potentially disabling critical infrastructure for weeks or months. Even milder storms in 1989 have caused catastrophic failures, most famously in Quebec. Yet preparedness is improving. Space weather forecasting has advanced with space-based solar observatories such as SOHO, Stereo, and DSCO-VR, giving forecasters hours to days of early warning. Models of geomagnetic induction allow grid operators to map locations most at risk, install Hall sensors and monitors, and, in some cases, temporarily shut down vulnerable transformers as the storm arrives. Satellites are equipped with radiation-hardened electronics and redundant systems, and operators have developed protocols for putting spacecraft into safe mode during high flux periods. What would it take to make civilization truly resilient to the largest solar storms? A multi-layered approach is needed. First, higher investment in forecasting and early warning ensures that there is precious time, hours or days, to act. Grid infrastructure must be assessed and systematically upgraded, especially long transmission lines in high-latitude regions, which are particularly susceptible to geomagnetically induced currents. International coordination ensures spare large transformers are pre-manufactured and warehoused, ready to be deployed rapidly. Backup communication systems, both terrestrial and satellite-based, must be robust against radiation, with protocols for fallback to analog systems in case of severe outages. Urban planners incorporate distributed energy solutions and microgrids into the core design of new neighborhoods, ensuring isolated pockets of resilience. Communities drill for disaster scenarios, including not just earthquakes or storms, but also space weather events. Schools include solar storm awareness in science curricula, demystifying the risks and empowering the next generation to innovate. The narrative of a giant solar storm ends not only with repair, reconstruction, and reflection, but with a recommitment to scientific observation. The sun, ultimate provider of heat and light, is also a source of awe-inspiring and sometimes terrifying power. As humans gaze outward, seeking to live on other worlds, it is clear that space weather will shape not just the fate of satellites and power grids on Earth, but the possibilities of life and technology throughout the solar system. Building resilience to solar storms is a necessary step in the ongoing project of civilization. In that sense, a massive solar storm, while a source of profound disruption, also acts as a catalyst. It challenges the world to adapt, to deepen its scientific understanding and technological resilience to cooperate across borders. It reminds us that technological progress brings with it new vulnerabilities, but also new opportunities for solidarity, innovation, and growth. The lights that danced over capitals and countrysides the night the sun reached out, for better or worse, left humanity changed. Not destroyed, but awakened, more alert to the intricate forces of the cosmos and to the remarkable, fragile world we share. Thank you for watching the video. What do you think about today's topic? Feel free to share your thoughts in the comments below. If you enjoyed it, don't forget to like and share the video to support the channel. Thanks again, and see you in the next video.